A wonderful good afternoon, ladies and gentlemen. Welcome back here at the Technical Forum at the group exhibit Hydrogen Fuel Cells and Batteries, this year in 2015 at the Hanover Fairground. Every 15 minutes, I invite you to come here and have a seat, enjoy, relax. There are drinks on the house. There's a lovely lady walking around serving you with the drinks. We will hear interesting presentations regarding the hydrogen and fuel cell industry. Also, at this time, I would like to say good morning, good afternoon, good evening to all our online guests. We are live streaming from this fair. Not only 150 exhibitors from 25 different countries here, we also have people watching from all over the world at this time. My next topic will be the Spectracarb porous graphite materials for specific electrochemical applications. Sounds difficult, but we will soon hear what this is all about. So please welcome with me on stage Managing Director at Engineered Fibers Technology, Mr. Bob Evans. Big hands, please.
Thank you and good afternoon. This morning I would like to talk about, or this afternoon I would like to talk about the development of Spectracarb porous graphite media. And in that title, I mean all the various types of porous graphite media materials that are used in electrochemicals. They might be called gas diffusion layers, they might be called current collectors, maybe called electrodes, but they're all really all based on a conductive porous graphite material. Just a little bit of background. Our company is Engineered Fibers Technology. We were founded in 1998 by a group of us who came out of various engineered materials disciplines. We are located in Shelton, Connecticut in the United States and approximately 100 kilometers northeast of New York City. But while we were founded in 1998, the Spectracarb material actually goes back to a much earlier time and was originally the development of a company called Spectracorp, founded by Mr. Jerry Fleming in 1991. And from 1991 until 2005, Spectracarb was a leading producer of gas diffusion layer products for commercial applications under the Spectracarb designation. And they were also a leader in the development of new gas diffusion layer materials, working with Department of Energy contracts and automotive and industrial sponsorship. In 2005, Engineered Fibers Technology acquired the Spectracorp business and has grown the Spectracarb porous graphite materials through engineered materials research, our wet laid paper development, and our specialty fiber investigations. Up until a few years ago, this work has been mainly focused in the United States. In 2013, we formed a partnership with Caplink Europe BV to be our technical sales representative in Europe, and they are located in Amsterdam. In all cases, our focus has been on technology that is customer driven and is customer responsive. That makes us different, we think, than some of the other products that might be on the market. And we'll touch on that as we go through the rest of the presentation. There are a couple different ways of making so-called gas diffusion layers, porous graphite materials. One involves either a woven cloth or a non-woven needle punch operation, shown on the right side of the operation. Those are usually continuous roll good materials. And the second way to make these materials, which provide a little bit different properties, is shown on the left side, and that's using a wet laid paper process, resin bonded carbon process. And in that case, we either make flat sheets, or we can make roll goods. In our case of engineered fibers technology, we are making flat sheets. This is a general diagram of the wet laid paper process for making gas diffusion layers. And my purpose is not to go through all the various steps, but basically to show you that there's a tremendous amount of versatility built into this process, anywhere from the type of fiber that's used, the length of the fiber, the diameter of the fiber, through the types of additives, the types of resins, the molding conditions, and so on, until we have a final product. I think the key to the wet laid process is versatility. It's an extremely versatile process, as I said. It allows you to use a wide range of fibers, particles. You can control the thickness, the density. These materials can be made on the laboratory scale, as small as say 20 by 20 centimeters, or they can be made on production or pallet scale. And small production runs, which is what we need for specific customer requirements, are easily obtained in this process. The photomicrograph of the Spectracarb gas diffusion layer. You can see it's a very open, porous structure. It's about 75% porosity in this particular material. Provides high conductivity, good strength and durability, in addition to all the other features that you need in a porous material as far as air permeability, water management, and other features, compressibility and so on. I should say, when we look at the wet laid process versus the non-woven or the cloth process, the one big difference is the compressibility. The woven and non-woven materials are much softer and much more compressible, whereas the wet laid process produces a much more rigid material. We have three main focuses in our business. And the first one, carrying over from Spectracarb, was to provide lower cost products that are interchangeable with other existing standard grades. The second was the development and the commercial production of gas diffusion layer products meeting specific customer requirements, designed to specific customer requirements. And that is the focus of what I want to talk about today. And the last is joint development engineering programs with some of the various customers of electrochemical devices. Just one slide, 2 slides on the low cost. This is a somewhat older slide, but I wanted to demonstrate we have produced in large quantities. We were part of the demonstration bus program with both the 2008 Olympics and the 2010 World Expo with Shanghai Shenli, where we provided well over 10,000 sheets of material for that program at a good performance and the lowest cost of all the materials that were evaluated. That particular material was a product that's called 2050A0850. It's about a 200 micron, 0.5 density material. And you can probably see it's very similar to some other first generation materials that are still used today. The area I really want to talk about is the development of special products focused on specific commercial applications. Now, we look at all the commercial applications or all the potential applications out there, from fuel cells to redox flow batteries to electrolyzers to humidifiers to electrochemical reactors. And no one, I think, is going to expect that one particular material or even a family of materials is going to necessarily address all those needs. So it really says, again, you need to be specialized. and address the problem at hand. Let's first of all just take a quick look at a PEM fuel cell. Obviously, on both the cathode and anode, gas diffusion layers are used. But how do we modify those, or what can we do with the kind of technology that we can supply to address some particular issues? This is kind of a composite slide, but if you look at the areas that are outlined in red, that represents a study that we did with GM several years ago, where there was a question of looking at the temperature of graphitizing or carbonizing the paper versus the performance to see what the cost-performance trade-off would be. And in this case, we were able to actually demonstrate, maybe somewhat disappointingly, that while we were able to get a 5% decrease in the cost, the overall cost of production of the fuel cell assembly, we had a 20% decrease in the performance if we went down to temperatures like 950 degrees centigrade versus a standard temperature of around 1750. But it was done very simply. It was done on laboratory sheets with, the study was more involved in that, and there's a reference to that particular study. But that was sort of the crux of the study. The blue photomicrographs just demonstrate that we can make materials with a lot more than just carbon fiber and phenolic resin. And a good example of that is a result that came out of some of the work we did with GM, where we were able to develop a water management system for the fuel cell stack based on the fact that on the cathode side, we used a standard material, standard porosity material. But on the anode side, we developed a special grade containing not only carbon fiber, but containing, and this is in a patent so I can disclose it, a graphite flake, and even some of our F-Tech microfibrillated, nanofibrillated fibers, which you can kind of see closely in the background. So that, again, is another example of how one can engineer a product for specific applications. Redox flow batteries are another area, very similar to fuel cells, but somewhat different and requiring some different characteristics. Now, I've borrowed the next two slides with the permission of the University of Kentucky and Dr. Stephen Lipka, showing some of his work on redox flow. And I won't go into all the points. We all know the advantages and some of the things of the redox flow battery. But coming out of that was a baseline of a Spectracarb 1550 paper that has shown the better performance over felts and the best performance of the molded papers, but not what we want. We still want more, and so now we're going back in and looking at modifications specifically of that particular grade. And interestingly, we add to that the literature references show that the porous carbon papers are better than the felts, and 1550 is better than the other commercial papers. And you look at some of the other literature references, it really says going thicker is a better opportunity to obtain better performance. This is now one of the directions we're going with that program of density and thickness variations. And again, that was slightly thicker material of a 350 micron, 0.5 density. And then moving over to electrolyzers, PEM electrolyzers. Another major area, and certainly an area that seems to predominate a lot of the activity at the last three hydrogen shows that we had the privilege to participate in. The we all know that with the electrolyzer operation that we can't use carbon, porous carbon on the anode side, and titanium is used. But on the cathode side, graphite papers, graphite panels actually provide significant improvement in opportunities. Number one, and which is always at the top of the list, it's a lower cost alternative to titanium mesh and sintered titanium. We can make thick panels up to 5 millimeters. We can make them larger than that, but we've made them up to 5 millimeters with densities, controlled densities anywhere up to 0.9 or even up to 1 gram per cc. You get very high bending stiffness out of these solid panels versus a stack of thin papers, which would be almost like a stack of playing cards. And these thick graphite panels really also function as elastic springs to help put the compressive load onto the membrane and onto the stack, whereas a titanium is not going to be compressible. And it's even possible to make hybrid constructions in those materials. And if we look at a simple plot of looking at the density of the paper on the x-axis and the thickness of the paper on the y-axis, you'll see that if we look at all the materials that are out there, commercial materials, whether they're papers, they're cloths, they're felts, they're the thin versions of Spectracarb, they all fall down in this box where we're from about a 0.2 to a 0.5 gram per cc density, and we're less than 500 microns in thickness. Where we want to be and where the electrolyzer supplier wants to be is up in this area of higher density, thicker panels. And that's an area that that we have focused very heavily on in working with the electrolyzer suppliers to make products to their specific needs. As I said, these thicker panels really behave as elastic springs. You can load them up to 20 or 30% strain, compressive strain, and cycle them several times, and obtain relatively good repeatability. First cycle is always a little higher than the rest of the cycles. There's always a little bit of a break-in with anything. And then finally, there's two other areas that demonstrate where specific designs can be made. Humidifier is a good example. Humidifiers, people were using carbon papers, but why use carbon when one of the features you don't need in a humidifier is conductivity? So why not use a glass or a ceramic? You're not graphitizing it, so you have to be very careful on the purity of the bonding resin that you're using. But you can make, and we have made, and there's a patent on this, of using glass and ceramic fibers in place of carbon. And then finally, on some of the electrolyzers for chemical electrolysis, they're exactly the same as we want for water hydrolysis, but we're not operating at the high pressures. We need a more open structure, and that can be obtained by the design of the material. And then finally, we would be very happy to talk to anyone concerning their ideas or their needs for working on next generation products. Cost reduction is always an issue, but on other concepts. And with that, I thank you very much for your time and attention. If anybody would like to discuss any of their special needs with us, we're directly behind you in stand C40-4. And again, I thank you for your time and your interest. Thank you.
Thank you also from my side. I have to apologize, there is no time for questions at this moment, but thank you very much. And again, you can be visited at booth number C40-4, just across the booth. Yeah. Thank you very much.
Thank you.
In a few minutes' time, we will discuss air bearings. We'll test the high-speed solution for fuel cell blowers, and for that, we'll hear the sales manager, the European sales manager of the Westwind Air Bearing Company, Simon Dack.